Welcome to another session of our reading group on the assumptions of physics. Today we're going to continue the exploration of combining domains. So let me share and give a summary of where we are. And let me put the link in the chat as usual. Done. And so last time we saw, we talked about the idea of combining domains. So you have a bunch of verifiable statements, say, on vertical position, a bunch of statements on horizontal position, and you put them together to get a bunch of statements on position on the plane. And we saw that in general, when you're combining domain, the possibilities of the combined domain are a subset of the Cartesian product of the possibility of the domains. And this is because the domains might have dependencies. So, and this is what we're going to actually look at today. Depending on what dependencies are there between the two domains, you get a different type of product. So let's get started here with the independent domains.
Independent domains. A special case is when combining two independent domains. For example, the domain for the pressure and the domain for the volume of an ideal gas are independent because the measurement on one tells us nothing about the other. Similarly, the domain for the shape and the domain for the color of an object are independent. In these cases, we can have any combination of any possibilities. Any pressure with any volume or any color with any shape.
In terms of topology, the possibilities of the combined domain are the Cartesian product of the possibilities of the original domains, and their natural topology is their product topology. We have a footnote. And note that the topology is quite naturally the product topology and not the box topology. The box topology would require countable conjunction and is therefore discarded. The fact that the correct topology is the one most natural to define confirms again the appropriateness of our framework.
This makes sense if somebody has studied topology, and if somebody hasn't studied topology, then they don't know what the box topology is. It doesn't matter.
Okay, so now we have the figure, yes?
Yeah.
So domain independence and projections. Given a population, the number of male and female members form independent domains. Knowing something about one value tells us nothing about the other. Pictorially, a constraint on one side gives us a vertical or horizontal band, which projected on the other axis give us the full axis, i.e. the certainty. On the other hand, the total population and the number of males are not independent domains. Given the total population, the number of males cannot exceed that number. Given the number of males, the total population cannot be lower than that number. Pictorially, we see that the combined domain does not span the whole plane. A constraint on one domain gives us, when projected, a constraint on the other domain.
So if you recall, when we were talking about independence of variables when we were doing classical mechanics, we had essentially the same pictures, that when we were saying that degrees of freedom were independent, we meant this. We meant the fact that any possibility on one side does not constrain the possibilities of the other, which is again different from statistical independence. Statistical independence means that you have a distribution, and the joint distribution is the product of the marginals.
Okay, so we have our definition. The experimental domains of a countable set dxi, where I ranges from 1 to infinity, are independent if taking one verifiable statement s of I in dx from each domain always gives an independent set of statements. And so
if you have a bunch of different domains, you pick one from each of them, and then they're independent, meaning, if you remember, if I pick a possibility, a possible value for one statement, a possible truth value, I'm not constraining the others.
Mm-hmm. And our proposition. So we have another sequence of another countable set of independent experimental domains. and xi are their respective possibilities. The set of possibilities x of the combined experimental domain, which is the Cartesian product, consists of all the possible conjunctions of the possibilities of each domain. That is, x is equal to the set of conjunctions of xi where the i's range from 1 to infinity. So we're taking a conjunction of each of the possibility from each domain, I guess. Notationally, we write d sub x equals d sub Cartesian product of all the xi's.
And again, recall it has to be countable because otherwise this conjunction would not be well defined. And you can see that all these conjunctions are not impossible because there is the independence. So if you fix one, you need to be able to have both possibility, the one where there is true and the one that is false. And so you basically get the whole domain. So we said that we wouldn't go through the proof, even though the proof is very short, and we can look at the next definitions and propositions.
Okay, let the sequence of xi's, ti's, so I assume topologies, be a countable set of topologies. Yes.
Topological spaces, yeah.
Topological spaces, yeah. Let X be the product of all the xi's, the Cartesian product of these points. Then let B be the collection of sets of the form, well, Cartesian products of UIs, where each UI is an open set from the respective space Ti, well, topology Ti, and UI is not the full space only finitely many times. Okay. The topology generated by B is called the product topology. Okay.
So this is how the product topology is defined. You take the Cartesian product, then you take sets from each open sets from each from finitely many spaces, and that set is an open set. It's a basis for the product topology. And the important thing is you can't take infinitely many open sets. You can only get finitely many open sets.
Okay.
Again, if you study topology, you would say, oh yes, this is the standard definition. And if you haven't studied topology, you're not gonna be able to study it like that in 1 minute. But the point is that this is the definition. And then the proposition tells us that if we have countable set of independent domains, the natural topology for the possibility of the combined experimental domain is the product topology. Yeah. So that's basically the result. And so again, you can think, instead of thinking of this construction, you can think that you have verifiable statements, one from each different domain, and you're just making the conjunction. And that's it. So it's the closure that we had before. You just take all the statements that you have from all the domain, you put them together, and you close under finite conjunction and countable disjunction. That's it. That's it for the independent domain. There's really nothing else. That fully characterizes the space.
Okay, dependent domains. Another special case is combining a domain d sub x with another d sub y as a subset of dx that is dependent on it. For example, combining the domain for the temperature of a mercury column with a domain for its height. Since the height can be determined by the temperature, no new possibilities are added. The combined domain is equivalent to the independent domain d sub x, since all the verifiable statements in d sub y have equivalents in it. And we have a proposition. So let d sub x and d sub y be two experimental domains such that one is subset of the other. Then Yeah, the Cartesian product of both domains is equivalent to the larger one.
Yeah, the combined domain of the x and the y is the x.
Mm-hmm. And then corollary, let d sub x and d sub y be two experimental domains such that one is subset of the other. The possibilities of the Cartesian product of both domains are the possibilities of the larger one again.
Yeah. And yeah, that's it. There's nothing much
Very
else
quick.
to say.
Okay. Incompatible domains. The last special case we consider is when the domains are incompatible. That is, all verifiable statements of one are incompatible with the verifiable statements of the others. This is one case where the residual possibility behaves differently from all the others, and we have a footnote. In fact, this is what prompted us to introduce the residual possibility. Okay, makes sense. Suppose dx, or d sub x, is the domain to classify a particular specimen as an animal, and d sub y is the domain to classify it as a plant. If we take a verifiable statement from the first, such as that specimen has fur, then it will be incompatible with the verifiable statement from the other, such as that specimen has lobed leaves. The only way we can combine the possibilities is to take an established possibility of one, e.g. this specimen is a cat, and combine it with the residual possibility of the other, e.g. this specimen is not a plant. In other words, the combined possibilities are the union of all the possibilities of the two domains, right? All possible plants and all possible animals. In terms of the topology, the established possibilities of the combined domain are the disjoint union of the established possibilities of the original domains, and their natural topology is the disjoint union topology, or the coproduct topology.
Definition 2.23. Two experimental domains dx and dy are incompatible if all verifiable statements in one are incompatible with all verifiable statements of the other. Formally, Sx is incompatible with Sy for each pair of verifiable statements Sx and dx and Sy and dy. Corollary, let dx and dy be two incompatible experimental domains. Then they must be incomplete and admit a residual possibility.
This is simply because otherwise you would have, if it were be a statement in one domain that it's comparable to two things that are incompatible, you would have some essentially some negation somewhere, and you would need you wouldn't have the residual possibility anymore, because you would have two open sets that essentially cover the full space.
Mm-hmm.
So you need to have the residual possibility, you need to have a point then that is never in any open set.
Mm-hmm. Okay, proposition. Let dxi be a countable set of experimental domains pairwise incompatible, and xi dot their respective established possibilities. The set of established possibilities x dot of the combined experimental domain, which is the product of the d xi's, consists of the disjoint union of the possibilities of each domain. That is, x dot is, well, that's how we denote disjoint union.
That's a disjoint union, yeah.
Okay. Which is of all the xi dots, which is, however, the same as the union because they are already disjoint.
Because they're different, yeah.
As well, yeah, they are all disjoint for all I and j that are not equal. So we denote dx as d sub disjoint union xi.
Yeah. And again, here it just shows that idea that whenever you are combining a possibility with another, with a Cartesian product, the only one that is going to be compatible is going to be the residual possibility. So you take an animal and not a plant, and a plant and not an animal. So you keep doing this and you construct all possibilities for the whole domain. It's just tedious demonstration, but that's conceptual. That's what's going on.
Okay. Definition. Let xi ti be a countable set of topological spaces. Let X be the disjoint union of the points. Then the disjoint union topology T is the topology for which U is element of topology if and only if the intersection of U with Xi is an element of what is it? Of the topology of this subspace. Yes.
Yeah, that's just the definition of the disjoint
Yes.
topology. Again,
Okay.
taken from a textbook.
Yes, and the disjoint union topology is generated by closing the topologies of the initial spaces under disjoint union.
Yeah. And I think that's, I know there is another one.
Okay, so one more proposition. Let D sub xi be a countable set of pairwise incompatible domains. The natural topology for the established possibilities of the combined experimental domain is the disjoint union topology of the natural topology for the established possibilities of each domain.
Yeah. So this is the sort of the result, and there is the mathematical demonstration there.
Okay.
Anybody who wants to double check that I'm not saying nonsense.
Okay, I'll finish this. For
Yeah.
topologies, as well as for other mathematical structures, we can choose between two types of products. If we have two one-dimensional Euclidean spaces, we can decide whether to take their product, either the plane, or the co-product, either the disjoint union of the two lines. For experimental domains, we do not choose. It is what it is. There is no way to combine the two experimental domains for temperature and height of the same Mercury column and get the Cartesian product of their possibilities. Though combining two independent domains mimics the categorical product and combining two incompatible domains mimics the categorical coproduct, it is the semantic and ultimately physical relationship between them that decides which product we have. This is another case where the mathematical structures forget the full equivalence. The topology only captures how the temperature and height can be measured, and not whether they are independent, dependent, or incompatible. That information lies outside of the topology and therefore needs to be added by choosing the correct combination.
And this is what we said the other time, that it's the logical context that is able to tell you which type of relationship you have. Now, here we only saw essentially three cases. In principle, there could be everything, right? There could be two domains where in some part they're dependent and in some part they're independent, or even more complicated. So what it hasn't been done here, it's try to categorize what is the space of all the possible relationships that a domain can have, like then two domain can have, right? So if I have two domain, what are the and I fixed the two topology. What is the set of possible combined domain that one could have that would give me those two domains with those two topologies? That's an open question. I have no idea how that works.
Okay, so section 2.3, experimental domain for experimental relationships. Now that we have seen how to describe relationships between domains, we should ask, are experimental relationships themselves something we can experimentally verify? We may know that there is a relationship between the temperature of a mercury column and its height, but how can we confirm experimentally which one it is? The main result of this section is to show that, given two related experimental domains, we can always mathematically construct from them another experimental domain for which the possibilities are continuous functions between the possibilities of the original domains. This means that since we can recursively create relationship domains about relationship domains, the universe of discourse of our mathematical framework is closed. Yet, the availability of the experimental tests, that is, whether the statements we construct are actually verifiable, is not guaranteed. First of all, we have to clarify within our framework what it means to experimentally verify a relationship. Suppose dx is the domain for the state of a light switch, up or down being the two possibilities, and dy is the domain for the state of the light, which can be on or off. Suppose we would have three cases. One where the switch is wired correctly, up corresponding to on, one where the switch is wired incorrectly, up corresponding to off, and one where the switch is not actually wired to the light and the two domains are independent. Each of these cases is represented by a different set of logical relationships and a different set of possible assignments. So we have these truth tables.
So this is where your switch is wired correctly. So these are the only two possible assignment. If up is true, on is true, and the other one are false. Otherwise, the opposite. Here you have up and off are true, or the opposite, and here you have all four combinations.
I guess I can finish this paragraph. Each case then is a different model, a different logical context. To experimentally verify which model is the right one means verifying statements of the type, it is possible for the switch to be up while the light is on. This does not correspond to the switch is up and the light is on, but to the switch is up is compatible with the light is on. These are statements about the table, and they cannot be columns of the table itself. What we need is to create a meta context in which each line corresponds to one choice of model to one context.
Each line will tell us what statements are compatible, and given the truth values of the line, we can reconstruct the model. The verifiable statements that distinguish between different models therefore live in this meta context, and so will the experimental domain for the relationships.
Okay, so now we have on the table, up is compatible with on, so they can be true at the same time. Down is compatible with on, up is compatible with off, and down is compatible with off. And then if we're in the first case, then up and on can be true at the same time, down and off can be true at the same time, but down and on and up and off cannot be true at the same time. The case 2 is actually the converse, and the case 3, everything is compatible with everything. Right, so this is what, if you remember at the beginning, we were saying that you couldn't really make that these statements, right, of compatibility and so on were outside of the logical context because they were assumptions in the model. And now we're basically going up and in direction making models of models, right? And these are exactly the type of thing that you do in science. You have different types of model at a particular level, and you're testing that particular level.
Okay, let's go next definition. Let S1 and S2 be two logical contexts. Let S1 be a subset of that, and S2 another subset of S2. Sets of statements. Okay. We say F from S1 to S2 is a logical homomorphism if it preserves the logical structure. That is, possible assignments on S2 correspond to possible assignments on S1. Meaning if A2 is in the possibilities of S2, then there exists an A1 in the possibilities of S1, such that both S and f of S get assigned the same truth value by these possibilities.
Right,
Well,
so if you have a way to assign A2, right, then you must have a way to assign N1 such that when you pass through a function, you actually can implement that assignment.
yeah. Okay, and then a verifiable statement of S1 is also mapped to a verifiable statement in S2. Additionally, if there exists a logic homomorphism, G S2 to S1, such that F G is the identity on S1 and GF is the identity on S2, then F is a logical isomorphism and G is the inverse of F. Two logic isomorphisms, F from S1 to S2 and G from S1 to S2 are equivalent if their maps are equivalent to all statements. Yeah. Okay, corollary. Let H from S1 to S2 be a logic homomorphism. Then for every S bar in S1, a capital S bar is subset of S1, and a truth function FB on S bar such that A1 of S bar is, I guess, implemented by this truth function. For all possibilities. Then
then there is an assignment in the new space where everything works with the same Boolean function. So essentially, Boolean function one space become a Boolean function in the next space. And so, for example, the H applied to the negation becomes the negation of H. H of the end becomes the end of H, and H of the disjunction is the disjunction of H.
Okay.
So it's basically a logical homomorphism because all the Boolean relationships get mapped in the same exact way.
Okay. Then proposition. Let S1 and S2 be two logical contexts. Let S1 be a subset of the first, S2 a subset of the second. And F from S1 to S2 a logical homomorphism. Then let S bar be a subset of S1, S bar 1, S bar 2 be the closure of S1 and S2 respectively under arbitrary conjunction, arbitrary disjunction, and negation. Then if there exists a logic homomorphism F bar from S1 bar to S bar 2, then, well, such that F bar of S1 is equivalent to F of S1 for all S1 and S1, it is not unique. So I can basically extend uniquely to the closure. Okay.
So what is going on here? We have, so the relationships, right, need to exist in two different domains. So I have the domain in which the light switch is wired correctly, and the domain in which the light switch is wired incorrectly, right? The ands and ors I only able to do within each domain, right? Within each context. I can't take statement from the different contexts and just compare them because the operations are defined within the context. So I need a way to be able to look at two domains, two pieces of the context and say, oh, they have the same logical structure. Okay? And so the idea is I define this function by basically saying I have a function that maps elements from one context to elements of the other context. And while I'm mapping the logical operation on one side to the logical operation of the other side. Right? And of course, it's not necessarily true that I can just take a bunch of statements and this is going to be true. Right? And so the fact that I have a homomorphism is what allows me to say I can take things from one side and put them on the other side. So then I can recognize that the domain of the light switch in this context is logically equivalent to the domain of the light switch in this other context. And then I can say okay, I have domains of the light switches, I have domains of the light itself, and then I can analyze the difference in the combined domain because one is wired correctly and the other one is wired incorrectly. It's again trying to take something that in principle it's simple and create the mathematical machinery to be able to describe it, and then of course it always becomes more complicated.
Sorry, a short question about this. Since we introduced these maps to be able to compare what is logical structures in different contexts, so does it mean that basically the function or the mapping measures like what is it, the difference of the context? Like it has to be constructed from both contexts, yes? Otherwise, how can we just make this map? How can we construct it?
Right, so the map is gonna be there if these sets have the same logical structure in both contexts.
Mm-hmm.
Like clearly, for example, if let's say that this S1 represents a domain, as I said, lights on or off, or this represents the domain of, I don't know, a vertical position of an object, then clearly there's not going to be a logical homomorphism between the two domains, because the structure of the statement is completely different.
Mm-hmm. Okay, because I was thinking that if we're looking at the logical structure in a context, and in general, they can be completely incompatible. It generally could be that there is no mapping. But if there is a mapping, then it means that the contexts are compatible or even the same in some cases,
Yeah, at the logical level it would be the same. Note, in fact, that this is a subset of the context, right? We're not comparing the whole context. We're saying this subset of the context looks similar to this subset in the other context.
Okay.
Which is again, right, the full context of the light switch wired correctly and wired incorrectly are different. Or let's say wired correctly and not wired at all are different. But the domain of the light switch in both cases is homomorphic. You can go from one to the other, has the same logical structure.
Okay, thank you. Okay, so we have a fat definition.
Yeah.
So let's d sub x and d sub y be two experimental domains. The relationship meta context S of C of x and y between dx and dy over what is it? The total set of SIs is defined by the following construction. Let I be an index set.
So this is going to be a long definition because it's complicated. But the point is that Cx of I, that's the set of continuous function. So we are basically taking two experimental domains and they are trying to define the set, the domain that it's where the points are the set of continuous functions. And so you are going to have a different contexts for each possible continuous function between the two domains. So in each logical context, you will have a copy of the two domain and a relationship between them that is given by a continuous function.
Mm-hmm. Okay, so should we still read it?
Maybe I can go through it. And
Yes.
so again, it's one of those things that becomes a little bit complicated. Quite frankly, I don't even know if this is the best way to do it. There might be a more clever way where all of this becomes much simpler. It's not something that I use a lot. It's just the purpose of this is just to show that in principle, once you define the experimental domain like this, you always have experimental domain for relationship, and so you never go outside of the framework. That's basically why there is this section. So there might be a better way to do it, but this does the job of what I need to demonstrate. So let's see if I remember what I was doing. So okay, so we have essentially dx and dy. We have a set of possible contexts here. So let I be an index set. Okay, so it's just essentially the index of possible relationships. And let Si be an index set of logical contexts. So these are all the logical contexts. And then let dxi and dyi be two index sets of experimental domains. So these are the copies of the experimental domain in each context, such that dx and dy are a subset of all Si, and let Fi be a set of logical isomorphism such that you can always go from dx to dy. So essentially, all these dxi's in all the logical contexts have the same logical structure. So if one, for example, is a position, a vertical position, so it's like the real line with the natural topology, all the others are real lines with a natural topology. Like they look all the same. And then you have a G for Y itself. So all the Y's also look the same. So now we have, let's say, the vertical positions and the horizontal positions, and they all look the same in all the domains. Now let S be the set of ordered pair of the X and dy, and Sx compatible Sy be the notation for an element of S for some Sx in dx and some Sy in dy. So we have the x and dy in the bigger context. For every two statement, we basically create this statement that it's the pair that asks, is Sx compatible with Sy? And then for each I, we can get a possible assignment such that the two things are compatible, right? So we're going to say that this is true if and only if the two statements are compatible. And again, we have to go from the meta context statement compatibility to an element of the truth value. So we are constructing this possible assignment. And so now we can define the set of possibility of our meta context as all these possible assignments that we have defined here. So basically, like the picture, we're taking all the pairs of all the compatibilities and then defining these assignment as in context 1 this is true, in context 2 this is false, and in context 3 this is true. So we're literally creating the domain for this table. And then what do I say? Assume that I have two things and they're different. If not, given a subset of I that leads to the same possible assignment, remove the assignment, but pick one. And basically this is we need to define a truth value, and we pick one at like there is going to be some truth value defined. Then what basically this does, it's now show that the possibilities are possible functions. So given an arbitrary function fb, we can extend the set S. I know this is just showing the closure in terms of the possible function that you can make. So given an arbitrary function fb, we can extend the set S with a new element for which the possible assignments are calculated according to the functions. And so the relationship context is the closure of S under all possible functions. So what happens here is that right now we just have sort of the product of these functions, but now you could make ands and ors and nots of all these of all the statements that have this as elements. So we need to create the context, we do the closure, and then we define the set of verifiable statements as these statements, that is X is narrower than Sy, that Sx is incompatible with not Sy, and like, well, these are all equivalent. So basically these are the things that we assume that are verifiable. So that if Sx and Sy are verifiable, we can verify that if Sx is true, then Sy is true. And those are the things that we define as verifiable statements. So basically the idea is we have a bunch of different contexts. They all have domains that look the same. And then from those contexts, we define a meta context where the truth values are defined by the compatibility of statements in each separate context. And once we have this humongous construction, we can then show that what we can we can define the relationship in meta context in terms of that things by taking these statements that we said that were verifiable. The fact when I can verify Ex, I can verify Ey. And then I'm able to define the relationship domain and all that. So I would probably just have you read this and the conclusion, which are the more wordy parts. The mathematically, somebody wants to go and look at it and nitpick in it. It's as I said, it's more complicated.
Okay, then I will read this. Now that we have the right context, we have to understand what is the right basis to generate the experimental domain. Suppose we have a way to verify experimentally statements of the type: the temperature of the mercury column is between 24 and 25 Celsius, and it's narrower.
Narrower, yes.
Then the height of the mercury column is between 24 and 25 millimeters. That is, we can verify that whenever Sx is verified, then Sy is verified. In that case, we can explore the connection between the two domains within different ranges at ever-increasing precision. This means we can narrow the range of possible functions in the same way that we can narrow the range of possible values for a quantity. These types of statements then form an experimental domain where each possibility corresponds to a possible continuous function between the two initial experimental domains.
Yeah, and that's basically it. That's what we're trying to construct. It's just mathematically complicated. And again, there may be a way to do it more easily. I don't know. But this is what I wanted to show, that you can always do that. And then there are caveats, which are these.
And note that the definition for the meta context simply declares some statements to be verifiable. It does not guarantee that this is actually possible. So when can we do it? Or better, what do we need in practice to be able to build the necessary confidence? Let's think how we would test the relationship between temperature and height of a mercury column. We would prepare different mercury samples with different values of temperatures in many different conditions, measure height and temperature with different devices, repeat many times, ask someone else to do it independently, compare results, and so on. At some point, we will have explored enough of the possible cases, checked and tried anything that could invalidate the result, and we will have the confidence to say that if the temperature of the mercury column is between 24 and 25 Celsius, then its height is between 24 and 25 millimeters. We should stress that the procedure is not at all to observe a few values and then generalize. It is not mere induction. It is the ability to prepare and control the system in many different conditions and our inability to violate the relationship that gives us the confidence needed to reach the conclusion.
Suppose, in fact, that we want to experimentally verify the link between inflation and money supply. As long as we cannot create new countries in different economic conditions, the only thing we can do is gather data for as many nations as we can throughout history. We have a footnote. Computer simulations sometimes alleviate this problem, though they are only as good as the model one uses. Since we cannot purposely explore different conditions and we can't even replicate older ones, the best we can do is show that there was a correlation between those specific values. It is the inability to freely and fully explore the problem space that may not enable us to experimentally verify the causal relationship. That's another footnote. In this sense, experimental sciences allow for more rigorous results than observational sciences precisely because it is more feasible to experimentally test relationships between domains. The point is that we cannot give a general purpose algorithm for how to construct experimental tests for the relationships starting from the experimental tests of the individual domains. We cannot formalize in general what it means to have explored the space enough to consider the relationship verified, no more than we can formalize when the data is collected enough, or to consider a statement verified, or when a statement is specific enough to consider the semantics well defined. This is where the practice of experimental science comes in.
But while we may not know in general whether we can experimentally verify a relationship between two specific domains, we do know that the relationship domain can always be constructed in principle, and therefore our mathematical framework is complete. That is, we can take two experimental domains, for example, dt for time, dx for position, construct a relationship domain between them, for example, dx of t for trajectories in space, then take another experimental domain, for example, dqp for the states, and construct another relationship domain between the two, which is d maps from qp to x of t, so points in phase space to trajectories. Yeah. Our general mathematical theory of experimental science is therefore closed, since we can recursively create relationship domains about relationship domains indefinitely while remaining within its bounds. In other words, experimentally distinguishable objects and their relationships will never lie outside of the theory.
And that's it. That's basically the main result. And it also, to me, it sort of clarified in my head why, again, physics can tell you more things than astronomy, which can still tell you more things than economics, because you can control, you know, the experiments and the setup more, and so you're gonna get, you're gonna be able to construct these domains, because otherwise we just know that there is some data and that you don't even know whether there are correlations, you have causation, or any of things like that.
What's the cardinality of the set of continuous functions? Do we stay like second countable?
Yep.
Nice. Okay.
Yeah, that's exactly the whole thing. If you have, so I probably should put them here, but if you have two second countable spaces, the space of continuous function between the two is still second countable. And I think it's also for Hausdorff. If you have the two Hausdorff spaces, the maps, the set, the topological space between the two maps are between the topological space of the space of maps is Hausdorff. There are like lots of theorems like that. And we can close it.
Yes, summary. In this chapter, we have seen the first important set of consequences of our general mathematical theory of experimental science. We have seen that experimental relationships between domains can be defined in terms of inference between verifiable statements, or equivalently in terms of causal relationship between possibilities. The causal relationship always corresponds to a continuous function in the natural topology. Moreover, it will need to preserve any additional mathematical structure that formalizes a physical characteristic of the domain. We have also seen how to combine a set of countably many experimental domains and how the combined possibilities depend on the logical and semantic relationships that exist across domains. Depending on the case, we can have the Cartesian product of the possibilities with the product topology, and all the way to the disjoint union of the established possibilities with a disjoint union topology. We have shown that it is possible to construct experimental domains for the relationships themselves. This means that within our theory, we can describe relationships of arbitrarily high order, relationships about relationships. And therefore, we never go outside of our framework. As we have only explored simple constructions based on the original concepts, these conclusions are of a general nature and therefore must apply to any area of science.
And that's it. So we can open it to questions and concern and whatnot.
So these possible relationships between things, I wonder how like the statistical inference basically fits in that. Like you would if you want to calibrate your thermometer, you basically want to establish the right link, right? You want to find the map from the height to the temperature. You would do that statistically. You have some measurement error or something. Is that something that's like completely like up to you? We don't formalize that at all. Or is it like, I don't know, do we get like bounds on it could be this map, or like we have open sets of maps. Like let's say we establish like it should be linear or something, then we would get open sets of slopes between,
Yeah.
right? And then the
Yeah.
more data we have, it would get smaller and smaller if we pick a confidence interval or something like that.
Yeah. So that's exactly how it works. But there is no statistics involved
Okay.
in this sense. So there is just the idea that you just improve the accuracy of your relationship measurements, and then you're gonna constrain more the slope and the the shape of the curve.
Okay.
So you can then construct sort of more statistical domains, but they always need to be constructed on top of the things which you're constructing the statistics of. Or if you start with the statistics, then the points are undetermined. So you are always going to have two domains that are related, right? One is the
Yeah.
domain of the statistics of the possible probability distributions, and the other one is the domain of where your probability distribution set.
Yeah.
And so the whole idea of the statistics is to create the ensembles, right? The ensemble spaces is where we would start to characterize the statistical objects, and an ensemble space is itself a domain with a topology and so on. So right now we are the only thing that we are saying is that we have the space of points, so the domains that have points, and those points could be statistical thing. We don't know. We don't care. They're just points
Yeah.
that we know how to measure approximately. And then we have a relationship, and the relationship between them is also measured approximately.
Yeah. Okay.
Maybe I have a question, but it is I wonder if it's more just coming from the fact that the words used are similar, but the origin is completely different.
Yeah.
So we were talking here about dependence of different domains and their compositions and other actions, and so me coming from relativity studies, there is also this entire language of domain, but in the causal sense. Yes, meaning that we had some system in the past, and we have it now, and we have it in the future, and then again we have the light cones, and then working with this let's say language, we can classify what where we can expect how to say some relationship, some direct causation, some and where we cannot do this at all. So I wonder, like of course, like here the story is a bit different, the origin story of this entire structure, but can this can we use this let's say this, let's say, alternative theory of topologies based on this experimental domains? Can we use this causation study, this to study causation of the physics itself, or is it really just as an argument to build, I don't know, set theory topology and rebuild all the mathematics? Because I'm trying to understand if this can be how to say lifted up from this very technical study of basically like point set topology.
Yeah, so you're gonna have to be able to reuse all of this to then remodel the everything. So for let's say that you have space time, right? So you have position and time. So that would be the domain for the events, right? At each point in space time is an event in the language of relativity, and then the fact that you have a causal structure and a causal distance and all that, it's other structures that you have because you have states, you have time, and time is a special variable because, for example, you want to be able to say that if I have a trajectory, right, an evolution, then that evolution is causal in the sense that if I know that I am on a word line given a point here, I know that I will be have another event, after some time. And so that's because sort of you have this time itself, right? You want time to not just be a variable that you measure, but it's also something that is related to the causal structure, right? And so it's actually easier to see it in phase space, right? You would have position and momentum as being your state space, and then we saw that I have laws of motion under deterministic and reversible evolution, which means I have a causal structure between those statements, because I know that if I pick a position and momentum at time t, there is going to be another at time t2 that is caused. So if I know that this is true, then the other one is true, right? And so that narrowness becomes exactly the causation, right? For each possibility at time t, I have one and only one possibility at time at t plus delta t. And so the idea would be to sort of to rebuild the math in a way that it's convenient, such that when you go and try to redo relativity, you're actually doing using the same definition without really thinking about it.
Yes, of course, that would it takes some effort, but I'm just trying to see if a bridge could be built. I don't know if you're familiar with causal set theory.
Yeah, well, familiar. I've seen some things, yes.
Yes, I wonder how this could be connected, because let's say if relativity already assumes more structure, well, causal sets should be how to say what they need is only this order and the nodes that are kind of multiplying or emerging. So it would be maybe more easier to track with your language here. But
I don't think that what they're doing in a causal set theory is compatible with this. So one of the thing that I've identified is that we cannot talk about causation in this physical sense, in the sense that I have laws, if you don't have ensembles in the first place. So this type of causation that we have here is very shallow, in the sense that it's basically just saying, oh, whenever I have something else. Like it's whenever I put the light switch up, there is the light, right? And there is that's not really a fundamental anything. It's just that in that context, with those given premises, you have those logical relationship, and that's it, right? What we are trying to say in when you talk about causation in relativity, it's something a lot more fundamental. You basically say every time that everything is set up in a particular way, you're going to have this limitation or whatnot, right? You can't really set up an environment in which you know, I have a light switch here and I have a light switch a million light years ago, and I switch it here, and oh, you know, those are the things that you're trying to do. And there is a sense that, and this I also talk to people who like work on causation and so on. I took them by side and said, okay, you know, you study causation. Can you think that, do you think you can define causation without some notion of ensemble, some notion of statistics, some notion of that? And all of them, they say no. Right? So even there is something called the do calculus invented by Pearl, which is one of these things to statistically inference and distinguish between correlations and causations. And the do calculus basically allows you to say, I have operations in which I fix some variables and see what happens. And with that, you can analyze if something maps to a causal structure. And you need the statistics to be able to do that. So the point is that you need a notion of an ensemble and relationship between ensembles to be able to even talk about causation. And so you need a bigger element. And that's what I'm trying to construct with the ensemble spaces. Like that there is a piece that it's that needs to be like well understood before jumping from one thing to the other. And I think the causal set is basically hiding that part. It's assuming some of this part, and of course, when you assume, you don't know exactly what you know, you're assuming that there can be causal relationship and they have some structure. But why do I need to assume that? I want to have all the details for that. Because one of the things that, for example, I don't even understand is, suppose that you have no access to deterministic and reversible processes. Can you create reference frames and then talk about motion and causation? Like, it seems to me that you can't. Like, whenever we define rods and clocks, there is an assumption of, oh, I built the clock in this way and it's going to be always this clock, and I built a rod, and that rod is gonna, in some sense, remain that rod. It's not gonna change in a way that I don't expect. And so there might be a chicken and an egg problem there. Well, but how do I define things reversible such that I can have this frame that continue, right? And I don't know how that works.
So then would not this problem transfer to the definition of units? When we are trying to define a meter in terms of some process?
Similar, yes, right. It's exactly that. You need to have access to some processes, and these processes define something, and then you compare everything else to those processes. And I don't know if you are just assuming that those processes are, you know, are stable in some sense, or you can verify that those are stable. I don't know.
Yes, well, I guess maybe it connects to this earlier question about temperature and height, when we do not have this, you know, exact result, but we might require some statistical criterion. I don't know, some maximum likelihood, whatever, chi-squared, one of them, to make this kind of a filter of what actually has been observed and what is still part of noise. So I guess we cannot really escape of it if we don't have access to these deterministic reversible processes.
Right.
But still, yeah, thanks a lot for the answer. I see that it's not as disconnected as I would imagine, but yeah, some work is needed, but well, good. So keeps us
there is
active.
the layer in between. So
Uh-huh.
the point is that this part just tells you that space-time is going to be a topological space. You're going to have some topology. It's going to be a manifold, and when you're going to have relationship between space and time, does it have to be continuous relationship at least, and so on. But this is not enough to then say I have a metric and all that. Right? The geometric structure is not the topological structure. And the geometric structure we have seen when we were doing reverse physics for classical mechanics. So the geometric structure was equivalent to the entropic structure. Right? If you have the geometry, you can get the entropy. If you get the entropy, you get the geometry. But the entropy is defined on ensembles. So it means that in some sense you are already assuming that there are some ensembles, that they have an entropy, and that entropy is giving you the geometry. So you need that piece. It's not just about observations. You need that piece, and that piece means I have some ensembles and I have some notion of variability within that ensemble.
Yes, I guess it's eventually we need some a reference, either physical or like model reference, but it has to be there. Otherwise, we cannot even start talking. And then when we have the reference, then we can start talking about, I don't know, anomalies, higher orders, and but then this connects, I guess, to this discussion we had where we are just making the statement narrower and narrower. So I think what it means is that we might never have reached the limit, but we have a process to control it.
Yeah.
Okay. Yeah. Thanks a lot for answers.
Yeah, and so those are all the things that I need help to figure out because I still haven't done them. So, okay, so it's after 10. If there are no more questions, we'll just close it and see you guys next week. No question from the chat, so we'll just drop it. Bye, everybody.
Bye.
Okay.